From space, Earth is often called the blue planet because so much of its surface is covered in water. But here on the ground, our perspective is more limited. We see the bay or the Pacific or the water in our homes. But let's connect those two perspectives, the everyday waters we know and the vast reservoirs that make up the global hydrosphere. In this video, we'll cover where water is found on Earth, including in our oceans, trapped as ice, which we also call the cryosphere, and in surface and groundwater. The Earth's oceans are the main reservoir or water storage system on our planet. 97% of Earth's water is stored in the oceans, and they cover 71% of the Earth's surface. They're all connected into one world ocean, exchanging water between them, but usually we humans divide it into 5 regions. In the Bay Area, we'll be familiar with the Pacific Ocean, but it also wraps around to the other side of this map, touching Asia. On the east coast of the US, we have the Atlantic Ocean, and then here's the Indian Ocean. At the North Pole is the Arctic Ocean, and surrounding Antarctica in the south is the Southern Ocean. Seas are smaller bodies of water attached to the ocean, and since they're connected and share the same water, we use the term seawater to refer to both. But seawater isn't just plain H2O, so let's look at what else is dissolved into it. In our previous video, we talked about how good water is at dissolving other substances, and how this leads to water being not just water. So if you've ever gone swimming in the ocean and accidentally got a mouthful, you know the ocean is salty. So salinity refers to the measure of dissolved salts in seawater, and the average salinity is about 3.5% of its total mass, which doesn't sound like a lot, but it makes ocean water undrinkable to us humans. And another key dissolved substance is carbonic acid. We talked previously about how humans are releasing CO2 or carbon dioxide by burning fossil fuels. And as more CO2 gets into the air, it also ends up in the ocean, dissolving into the seawater and changing its acidity. So this makes it difficult for animals with hard shells especially to survive, which also harms animals that depend on those hard-shelled species. So the chemistry of seawater isn't static. It's changing and it impacts ocean life. Another big characteristic we measure is ocean temperature. We often look at sea surface temperature to collect this data. It, of course, decreases further from the equator, either north or south, and at the equator, the surface can go above 80 degrees Fahrenheit, shown in red on this map. At or near the poles, it can go below 0 degrees Fahrenheit, which normally would freeze water, but the salt lowers its freezing temperature. We can see this cold water in dark blue. Like air, water also moves vertically up and down. To help think about this movement, we use an idea called a water column. So this is a vertical section of water spanning from the surface down to the seafloor. And in general, the bottom is denser because water above is pressing down on the water below. When water gets mixed up or out of order, the density of a water mass will affect how it moves within the column. And basically, it balances back out. So lower density water rises, and then higher density water sinks. So this sorting of layers is called density stratification. So what exactly controls the density of water? In many cases, density is being affected by salinity and temperature. And we can see this clearly at the surface, so here are some examples. When rainfall adds fresh water to the surface of the ocean, salinity goes down. With less salt and thus less mass, the water is less dense, so it stays near the surface. On the other hand, when it's sunny and evaporation pulls water away, the salt is left behind, and that makes the surface water saltier, denser, and more likely to sink. Temperature also changes density. In colder regions, water molecules will move more slowly and pack closer together, making the water denser so it sinks. And near the equator, warmer water molecules move faster and spread apart, so the water stays less dense at the surface. So overall, changes in salinity and temperature drive the vertical movement of ocean water. And not only does water move vertically, but it also moves horizontally in currents. This should remind you of the way air moves, because at the surface, ocean water is moved by the wind. We see warm currents in red, usually along the west side of oceans. This is because that warmer water is moving toward the poles. Inversely, we see cold currents, usually on the east side of oceans, moving toward the equator. So, for example, the California current moving along our coast is a cold current because it comes from the north along the eastern edge of the Pacific Ocean and moves toward the equator. But seawater doesn't just move at the surface. Water in the ocean is also moving below, driven by density differences. We call this thermohaline circulation because it involves temperature, where we get thermo, and salinity, which is where we get haline. In the polar regions, two processes make water denser. First, the decreasing temperature causes the water to cool and contract. And second, as sea ice forms, it expels salt, making the surrounding liquid water saltier and thus denser. So that cold and salty water sinks and flows along the seafloor, pushing water in a slow-moving global circulation pattern like a conveyor belt. And the water eventually makes its way to the Pacific and Indian Oceans, where it warms and rises. And this whole process can take about 1,000 years to fully cycle. So circulation is one way the ocean moves. Another way we see movement is through the daily rise and fall of sea level, what we call the tides. We often explain Earth processes through its relationship with the sun, but tides are interesting because they're mainly driven by the moon. The moon's gravity pulls on the ocean, creating these bulges in the sea surface. And we see high tides on both the side facing the moon and on the opposite side, while lower water levels appear in between. Locally, we can see this process through a pattern of water levels rising and falling about twice a day. There are some special tide patterns that get their own names. Spring tides are the highest of highs. It has nothing to do with the spring season, but rather comes from the Earth, Moon, and Sun all lining up about twice a month during the full and new moons. Neap tides are the lowest lows when the moon and the sun are at a right angle from each other. They kind of cancel out a little bit. So tides are another way that the ocean is always moving. The second biggest store of water on Earth is actually ice. We call this the cryosphere, the part of the hydrosphere that is frozen. And this is about 2% of Earth's total water, and it includes ice both on land and floating at sea. About 10% of the Earth's land surface is covered in ice. And so we can find this in mountain glaciers, in ice caps, such as the one covering about 10% of the country Iceland, and in massive ice sheets that cover whole continents. So there are two ice sheets in the world, one on Greenland here in the picture, and the other on Antarctica. And ice isn't only found on land, it's also found in the ocean. So unlike most substances, water becomes less dense when it freezes, which is why ice floats. So icebergs are these large chunks of glacial ice that break off into the ocean. And in polar seas, we also find vast flat areas of frozen seawater called ice pack, like the one that covers much of the Arctic Ocean in the north. Another form of sea ice is an ice shelf. These are flat areas of ice that extend off a continent, especially Antarctica, and just kind of hang out over the water as a shelf. So in this picture on the left, that ice isn't being supported by land, but it is connected to it. And Antarctica has many ice shelves, which we can see on the map here in green, and some are massive. The largest is larger than California. So floating ice ranges from these small bergs to enormous shelves, stretching hundreds of thousands of square miles. A smaller but important part of the cryosphere is underground ice called permafrost. The word combines permanent and frost, though it's not truly permanent, it's more like continuously frozen soil. Permafrost is found mostly in northern Canada, Alaska, and Siberia. And as global temperatures rise, permafrost begins to thaw, like in the picture. This isn't just a physical change, it has a big impact on climate. So frozen soil locks away organic matter, like dead plants and animals, keeping them from decomposing. But when permafrost melts, this material breaks down, releasing carbon dioxide and methane, these powerful greenhouse gases, into the atmosphere. So now let's turn to surface water, which makes up only a tiny fraction of Earth's total, about 0.02%. One example of surface water is lakes. These are bodies of water surrounded by land. So, for example, we have an aerial view of San Andreas Lake to the right here. This is that lake you can see to the west of Interstate 280. And most lakes contain fresh water, but some of the largest lakes contain salt water. Lakes are formed through a basin, so this low part of the land surface that has limited outflow and enough inflow to keep it partially filled with water. Some lakes are artificial and were made by humans to store water as reservoirs. So dams allow humans to control how much water comes out. And this is a picture of Hetch Hetchy Reservoir in Yosemite, which is where San Francisco and much of the eastern side of the peninsula gets its water from. It's piped all the way out to the Bay Area. And this is completely artificial. Humans built the O'Shaughnessy Dam here in the 1920s and flooded a whole valley in Yosemite. This was actually super controversial back then. But this was ultimately considered important enough to support a growing city like San Francisco. So reservoirs gave us this way to store and manage surface water. Another form of surface water is flowing water, so rivers and streams. In geography, a stream is any flowing water, which includes rivers, and a river is just a larger stream. So streams drain the Earth's land surface and move that water along with sediment and dissolved chemicals and minerals to the ocean. And they also provide mobility for humans when they're navigable, which just means that they're wide enough and deep enough for boats. So rivers and streams drain the land and connect inland regions to the oceans. But there's actually much more water stored as groundwater. This is any water held underground, and there is 36 times as much water underground as in lakes and streams combined. So groundwater relies on the permeability of rock, which just means the ability of rock or soil to let water move through it. And this water moves through small interconnected openings called pores. Groundwater is stored in aquifers, which are permeable rocks that allow water to move slowly through it. The map on the right here shows the aquifers just along the coast of California. There are also aquifers in the Central Valley. And much of the bay is surrounded by aquifers, actually. And the Santa Clara Valley gets a lot of its drinking water from groundwater. The opposite of an aquifer is an aquiclude, impermeable materials that do not allow water to move through them. To understand how aquifers work, we can divide the subsurface into distinct zones based on their role in the groundwater process. So let's take a look at a cross-section of the ground here. In dark brown, we have the aquicludes, those materials that water cannot pass through. And in light brown is rock or soil that water can move through. And we have the groundwater in blue, of course. So when it rains, water runs into the permeable rock. At the very top, we have the zone of aeration, directly below the Earth's surface. This zone has pores that are mostly filled with air, allowing rainwater to pass through easily. Rainwater that moves through this zone collects and builds up below, in the zone of saturation. Here, all the pores in the permeable rock and soil are filled with water, and the top of this saturated zone is called the water table. If the ground surface dips below the water table, the groundwater emerges as surface water, forming bodies like lakes or rivers. The water in this zone is prevented from moving further down by that aquiclude, the underlying impermeable layer. Below the aquiclude, you might find another area of water called the zone of confined water because it's trapped between two aquicludes. This zone is also an aquifer, permeable rock that stores water. And this water can be accessed by humans using a technology called an artesian well. The aquiclude is drilled through and the pressure in the aquifer is high enough to force that water up and out to the surface for humans to use. The artesian well is an example of groundwater mining, which is just the extraction of water from underground for humans to use. Groundwater mining is usually used to provide water for crops in drought years when the level of rainfall may be less than ideal. But one problem that comes with groundwater mining is called subsidence. This is the gradual sinking of land when water is pumped out of aquifers faster than those aquifers can recharge by rain. So the pores that were once filled with water can collapse, causing the land's surface to lower. On the right here is this famous photograph about subsidence. It shows a man standing next to a pole in the Central Valley, showing the ground level in 1925 at the top of the image and at his feet in 1977. So over about 50 years, the ground in this area sank 9 meters, which is about 30 feet. So subsidence shows the risks of overusing groundwater. So altogether, water is stored in oceans, ice, surface water, and groundwater, each with its own dynamics. Over on Canvas, you will find your assignment for this week. You will be taking 2 pictures of water, one where water is moving and one where water is being stored. Then, of course, share the pics in the forum, answer the posted questions, and reply to 2 or more peers. In our next video, we'll be combining the hydrosphere with the atmosphere and talking more about weather. So thank you for watching and see you next time.